Hello everybody, welcome to another episode of Analytics Mindset. In this specific video, we will be looking at a practical example of logistic regression, its assumptions, and also its uses. This will follow up to my data analytics computing follow-along logistic regression video that if you have not gone there first, I will strongly recommend you to go there. It will be somewhere in the screen. And if you have already done so, then I can go ahead and talk a little bit about that as well. To get started, this is going to focus on the implementation of logistic regression and some inference that we can do from the modeling side of it, instead of going the more programming side of things. However, I do recommend you to go to my programming basics video, that it will also be somewhere over here in case you're not that familiar with Python or you need a refresher on programming basics. With that being said, let's get started. This is used with the permission of other participants from the Virginia Datathon 2023 team. You can find the presentation that we put together for this, and this is regarding maternity data. We first start by importing some packages, especially NumPy, Pandas, PyPlot from Matplotlib, linear model, model selection, and Seaborn and SodaPy. Specifically, this is the package that would allow us to connect to the dataset that we're using right now. As I will show it right now, I will go ahead, import all these packages, as you can see here, and execute this. After I have my packages, I first need to create my Socrata client. I will do that by giving it an URL that is data.virginia.gov, and this is the dataset identifier. The client creates this by taking from SodaPy, Socrata, and you take the data URL, an app token that I created in the website, and then a timeout. And I will show you how that executes. Then we can see client. If we see the actual client, you can see that it is a constructor for SodaPy Socrata. This is a way to import data into Python. This is connecting straight into the database that we want to get the data from. This is not a data yet. This is not a data. It's a reference, a connection to the data, but it is not the data yet. For that, to get the data, first we're going to put the results from the get data here. We can see the results here. You can notice it is a very, very long dictionary of a lot of different items here. But I don't want a dictionary. I want a data frame. Then I will convert this list of dictionaries into a data frame by using the PD data frame function from Pandas from records by using those results. And now I can take maternity data. Just copy and pasting this just in case I do a typo. There you go. I have a data frame of these 1,000 rows and 24 columns. Now you can also get this through shape, as we have seen multiple times. This is just for exploratory purposes. Same thing here. We are having 1,000 rows here and 24 columns. With that being said, we are mostly focused on gestational age. We're going to get the unique values from there. How you will read this is you take the maternity data dataset, and then you only get this column, gestational age. And from there, I'm going to get the unique values for this. And as you can see here, there are not that many unique values. This mostly refers to when it was that the birth happened, basically speaking. We are going to recode this variable to at risk if it's before early term that was consulted with a subject matter expert, and 0 if it's low risk, being low risk, or 1 if it's high risk. This is a classification problem because of that. We're creating two discrete values of 0 and 1, yes or no, basically. I will take this, and what I'm doing here is using NumPy select. With the select here, I'm saying if the maternity data gestational age is in any of these three, then you're going to make a 0 here. Else, if maternity data, gestational data is in late preterm, very preterm, or any of other these ones, you're going to put a 1. And I will show you by copying this, pasting this here. And now we can look at the new gestational age risk variable here. You can see it has zeros, it has also ones, etc. And if we do unique, I have both zeros and ones. That is perfect. That is what I want. Then I'm going to subset the data frame to the variables that I'm actually interested in. As you can see here, there's 24 columns. I don't need all of them. I'm just going to subset these by the columns that I want to get. And to subset the maternity data set. And now if I do maternity subset shape, you're going to get way less columns than before. Only 15 columns here, so I got rid of 9 columns. I'm going to review that there is no nulls because sklearn cannot handle nulls, and I will need to handle that before. As you can see, none of these variables has any kind of nulls. That is good. I will recode the column. There's this column here called A and B utilization and prenatal despair here. I will show you how it looks like. False and true. If I multiply that by 1, though, it becomes a Boolean of zeros and ones, and we want that. Again, just mostly because sklearn, we want to make sure that we can read this, so we are just multiplying it by 1 to give us a Boolean value. If it's false, it will become a 0. If it's true, it will become a 1. Now, after that, we're going to subset the target and the predictors in different data frames. First, we're going to take the predictors. They're subsetting everything besides gestational age risk. We are taking that out. That is what this means. I'm saying they select all from there, from log, but do not select the column where the name is gestational age risk. So I will go ahead and put this here. And you can put predictors, 14 columns. And then I will put the target. I will just get that column here in the target. As you can see here, it's 0, zeros or ones. That is the gestational age risk. And it has a length of 1,000 because it's the original length. Now, there are a lot of variables here. And if we go back to predictors for a second, you can notice that a lot of these are categorical. So you have multiple text values for most of them besides these two, obviously. We are going to create something called dummies. Actual good explanation on dummies will take a whole video. I will leave some resources in the description, but what you need to know right now is that this will create a column per categorical variable to show you how many instances of data are there. So you can see here, our old data frame had only 14 columns, but that became 53 here. Why? Well, that's easy to understand actually. If we take this, we take this predictor summary shape, and then we put columns instead. We have for maternal age, whenever it's 16 through 17 years, 18 through 20, 21 to 24, etc., etc., etc. We are dividing multiple categorical columns for each of these different categories and creating a different column for that. That is what the make dummies is creating, the get dummies function is creating. Again, you can get way more explanation in the description of the video, but you are creating a different column, so sklearn can handle it and can say, here's a 0, here's a 1. Okay, how do we put this into true or false? And actually, if I go here to predictors with dummies, in the variable explorer, you can see that it becomes a very sparse matrix where I have a ton of zeros and ones based on each categorical case. Now from there, we're going to create a new logistic regression model with a random state to make sure that we can replicate this, even though logistic regression by itself is not really random. Let's play it safe rather than sorry. And then we're going to fit the model using the target and the predictors with dummies. Once we have that, now we need to see the classes. So I will take this and see what classes I have. As you can see, it's an array of 0 and 1. This is the actual prediction. This is what we are predicting with. In this case, because we only have 2 cases, yes or no, it is not that complicated. But this could be way more complicated depending on what we do. Now, the advantage of logistic regression, and most linear models, by the way, is that we have a lot of flexibility to understand what the model is doing. We actually get a formula. We can actually see what is happening instead of the most complex models like neural networks or random forests. It's just a very, very random black box pretty much that is fitting anything that you give. So we can get the intercept. We're going to do that, get the intercept of logistic regression, and we're also going to get the coefficients of logistic regression. If you were to write this formula as an actual, and these numbers as an actual formula will be, this is your intercept where you start, and each of these coefficients are the log odds of each of the columns that you have there, then how they impact to our categorical target. Now, there is a more powerful way to do this, and this is actually related to the train test split test that we saw a couple of videos ago, that I will leave you the link over here, that we can use a very powerful tool called cross-validation. What cross-validation does is, very briefly, you take the model, you train it in part of the data, and you leave certain cross-validated sites outside of it. And then you do that over and over and over again to each of them specifically. Again, an in-depth explanation about cross-validation is outside of the scope of this video because I am just focusing on this specific example of logistic regression, but it is a very powerful tool to measure with way more accuracy how much error do you have, how much can you expect your actual accuracy to be, etc. We're going to get the score then. We're getting here and cross-validating it for 10 and getting the mean from there. And we get 91% or 0.909. So that is an awfully good model, actually. This is a very good model. Very complex, though. It has a lot of coefficients and a lot of columns, but it's a pretty good model. Now we are going to get the coefficients of the model, and these coefficients don't work for me. This is just a mindless matrix of numbers. I don't want this. I want them to be somewhere with a label, with the actual column. sklearn, unfortunately, does not have a way that I'm aware of. If you find it, I'm going to be very glad to include it somewhere. But it does not have a very straightforward way to actually build that column score validation for the coefficients. Therefore, what I'm going to do is a more manual approach here. I'm going to first create a dictionary with all the coefficients. And from there, I'm going to use quite a bit of comprehension here, making for each coefficient in each feature in SIP of the logistic regression. So in each of these coefficients and predictor with dummy columns, you are going to take the first value of this coefficient, and you're also going to take the predictors here and then assign that feature to the coefficient. So if I run this for loop, and then I take the coefdict, the coefdict will tell you here, this is my column, this is the coefficient of that, this is the feature name, this is the coefficient of this. So this gives me a list. This gives me something to work at. Okay, I have something here. That's good. Then I'm going to go ahead and create a data frame from there because I just prefer data frames to dictionaries, being honest. I just like better how they look like. And it's called coefdf. There you go. Now you can see you have your index here, and you have here the name of these columns, and this is the coefficient in the logistic regression. This is not the coefficient that you will multiply in linear regression. Do not confuse it with that. It is the log odds coefficient. If you actually want to do a logistic regression calculation by hand, you need to take the logarithm and then see the probability, etc. It is a more complex model, but it allows you to get that categorical answer. Now, I'm going to calculate the standard deviation of each coefficient here. So I'm going to create a new column that is going to take the standard deviation with these and add it as a list. After running this, you can see I have added a new column. Here is the standard deviation of each of these columns. And what I'm going to do now is sort this, because this is not sorted right now. Notice the in place here, I'm saying is not ascending, so this is descending order, and it's in place, meaning it's going to replace the current data frame. So now coFDF looks like this. It is sorted, because here you can see it goes all the way from the coefficient, but you cannot see it here because it's being obscured by this. But you get the idea there. And now we're going to calculate the importance. There is a lot of ways that you can calculate the actual importance of a coefficient in a model. Future importance is calculated by other ways in other more complex models. For logistic regression, we are going to stick with this approach that we take the magnitude of the coefficient and we're multiplying that by the standard deviation of that column. And that is going to give us an importance of how much more or less this specific variable is important to the model. We're going to do this here. And then we're going to take coFDF again. And there you can see, there we have our importance here. Now we're going to filter importances here, and this is where another step on modeling comes in. We prefer simpler models to more complex models. I want to make this logistic regression model as simple as possible. Very complex black box models are very difficult to explain, and as I have explained before, they have their own disadvantages. If I can make a simpler model by losing very low precision, I will take that simpler model. So this approach is used as sklearn lags actual hypothesis testing, unfortunately, for coefficients with p-values that you could do in stats models that we will look in the future or in R. So we're going to do this. We're going to say the coefficient, the importance of the coefficient needs to be more than 0.15 or less than negative 0.15. Why? It is just a threshold that I said around 0. We want 0, it's basically representing 0 variance. It does not really affect the model, either positive or negative. It would be good because that means it's capturing a ton of that variation in a linear model, mostly logistic regression. But here, I want to get rid of everything that does not have a lot of importance. Either it has a very low standard deviation or the coefficient is pretty small, one of the two. I will go ahead and take this. And now I can take the new coefilter data frame. As you can see, I only have 11 rows, so that's 11 features. If you compare it with 53 that I had before, that is an awesome improvement. Now, we do not know how much this affects the logistic regression model. It is always good to double check it. If we were in linear regression, there is a more robust version of this called stepwise regression, where you have the model performing multiple hypothesis testing and try to go either backwards or forwards by either starting with an intercept and adding different variables, or having the whole model of the data frame variables and then discarding one each by one with hypothesis testing. That is something that we may look into the future. We are first going to get the filtered predictors. So these are the predictors that we actually want to get. And now if we see this, you can see them here. We have 11 of them. So we are basically filtering anything that is not in this list of predictors, in this coefilter. This coefilter, remember how it looks like? It looks like this. If we add that 0 there, we are only taking the names of it. And that's how we are using these to filter this. And you can actually go ahead and see what it looks like if we just take this with the to-list part of it. This makes it from a data frame into a list that then we pass here, and we're saying these predictors need to be in this list here. Now we're going to have a refined model. We are going to train a new model with the new variables. I'm taking this first. This is a new logistic regression. And then notice how here I use predictors with dummies. Instead of that, I'm going to use these filtered predictors because this is a way smaller path here. There's way less data here. That creates a logistic regression. And now I'm going to do the same here by replacing predictor with dummies instead with filtered predictors. And again, I'm doing a cross-validation score here by saying, take first the refined logistic regression model, then the filtered predictors, then my target that it hasn't changed, the target has not changed, this only affects the predictors, and then doing a cross-validation with 10 different, 10 cross-validated basically, and the mean of that. By doing that, 0.908. Now, remember that the last one was basically the same. We lost 0.02 on accuracy. That does not really matter. We're fine. But this model is way simpler than the one before. We have way less coefficients. We are doing the same thing. We're iterating through the whole thing and then getting the coefficients that we need. Do that here. And now if you put that into dictionary, from dictionary to data frame, and then we're going to take this data frame, and I will show you, we have way less predictors. We have shrunk our model way more to make it smaller. Now our smaller model is way easier to both understand and run too, because it will be more feasible to compute. So instead of taking the whole data frame, next time, if you were to build an ETL pipeline with this model, you will filter out for these filtered predictors and then ingest into the model. That will accelerate also how much time it takes. Even though this logistic regression is a very simple model, it is awfully fast, but still it will be an improvement there. We're going to sort it again. And now the main problem of this specific script was to identify what are the most important variables as identifying maternity modality. In that case, we use, as we are doing a visualization here, I'm taking SNS bar plot. I'm basically saying plot this for me. And I'm going to do it with all of these. So this is just a label. This is also just a title here. And PLT show allows me to actually see it. I will execute all of this here. And I will show it to you here in the plot. What is it showing here? Well, first, I'm saying these are the log odds coefficient values for the logistic regression model. Your probability of unfortunately dying at birth if you're a mother, an expecting mother, it is actually very highly correlated if you have very low weight. Your child has very low weight. There is quite a bit of them that do not make that much sense at first, but then you think about it and it actually kind of makes sense. If you have no prior pregnancy, it's a little bit higher chance. If you had prior pregnancy, it's a little bit lower chance. If you think about it, maybe it's also because the mothers are used to it, if it's a second or third pregnancy, etc. But as you can notice here, if the weight of your child are giving birth is not low, you have way less maternity mortality here. It is inversely correlated to it. If you want to understand the more statistical part of logistic regression, I highly encourage it. It is a fascinating model that allows you to basically model very complex relationships in a very simple way. It is not the best model a lot of times, and it does model it to the binomial distribution, but it is a very powerful model when you know how to catalog stuff and if you do not need a more complex model to model the relationship. In this case, it is more than enough, and this is what we presented there with all of this data and all of these relationships with maternity mortality. With that being said, I'm going to finish the video here. I do appreciate any kind of comments, feedback, comments, or likes that you want to give me. So please support my channel, and I hope to see you soon. Thank you very much. Have a good day.